So I decided I wanted to go ahead and take a look at the propagation delay through the 4 divider chains that we had set up. So to accomplish this, I'm using the logic analyzer that came with my Rhode&Schwarz RTB2004 scope. I've got 4 inputs set up on the pod here as D0, 1, 2, and 3. These are picking up the pins that are driving the LEDs. So it's I/O, I believe it's 21, 16, 15, 14. So they're plugged onto the board here. The grounds from each one of the inputs to the pod are of course grounded as well. This is really low frequency. I'm not sure that's critical, but it'll give me a little better signal fidelity. And of course, as I pointed to, I've got the logic pod here. And of course the USB blaster is just hanging out here from the last time I programmed. So anyhow, there's the setup on the hardware side. So I thought now we'd jump over to the scope and take a look at the actual propagation delay. So looking at the scope, we can see that we have 4 traces here from the logic analyzer, and it's the 1000 Hertz, 100 Hertz, 10 Hertz, and 1 Hertz signals. Let me take you through the setup on the scope so you understand what I did here. If I go into the trigger menu on the scope and I edit the pattern, what I've told the scope to do is it's a 16-channel logic analyzer down here, and I'm only using 4 channels, 0 through 3. So for the trigger setup, I've told it to ignore D8 through D15. I've told it to ignore D4 through D7. And to only look at D0, 1, 2, and 3 on a low-going transition. So we're only going to trigger on those 4 channels. We're going to AND them together, and they all need to go false. So that'll get us a trigger where the outputs all reset to a low. If I go ahead and close up the trigger menu, we can see here on the scope that actually that's interesting, the trigger point isn't exactly where I expected it to see it. I would have expected it to see it on all zeros. So not quite sure why the trigger point is actually on a positive going edge here, negative, negative, negative. That's probably something I've got wrong in the setup, though I'm not sure exactly what that'd be. Anyhow, I acquired this signal I wanted. I don't quite understand the slight discrepancy here, but what we can see is, like I said, the 1000 Hertz, the 100 Hertz, the 10 Hertz, and the 1 Hertz. And the idea was to zoom in on these negative going edges and just kind of get an idea of the propagation delay. If you remember, the Verilog code are always block triggered on clock, neg edge clock. So the neg edge of this clock triggers this stage to count. The neg edge of this clock triggers this stage. The neg edge of this clock triggers this stage. In this case, this is actually falling all the way through to where everybody comes back around to zeros. So let's go ahead and zoom in here a bit. Bring him back a little better to center. Bring him back a little better to center. And we can start to see here. So I'm going to get down to 2 nanoseconds per division, which is the highest resolution I have here. It's a 300 megahertz scope. So in this case, you can see that the 1000 Hertz dropped to 0. There's, I don't know, 1.8 approximately nanoseconds of propagation delay before the 100 Hertz dropped to 0. Oops. There's another approximately 1.8 nanoseconds before the 10 Hertz dropped to 0. And if we take a peek here at the D0, we can see that there's 3.2 or so nanoseconds before it came to 0. So you can see there was a propagation delay through the chain. This is bringing everybody back to a 0 count. So the place this probably triggered in the code would have been the block where we go in and we basically say, if we're at the max count, toggle the output and reset the count. So that's probably where this pulse chain come from. See, the propagation delay here isn't horrible. You know, it's sub 2 nanoseconds, sub 2 nanoseconds, a little over 3 nanoseconds. For what I'm doing here, circuit-wise, this would be fine, because ultimately these were just pulse trains meant to drive counters. I'm going to go in and capture a different trigger, and we'll take a look at it next. So in this case, I have set the triggering to ignore the 1 Hertz line, to look for a high transition on the 10 Hertz, a low transition on the 100, and a high transition on the 1000 Hertz. And went ahead and did a single shot capture, and again, I'm not seeing exactly what I wanted to see. There's the go high, the go high. So this probably triggered someplace back here, honestly, and I'm curious now if it triggered someplace. Well, it is. The trigger's off the screen here. So the point this triggered is moved off the screen. But I've gone ahead and captured this set of transitions here. We'll bring the triggering back to the center here in a second. We're now at 1 nanosecond per scale on the scope. And we can see that the delay, let me get him on center, is about 2.4 nanoseconds from the 1000 Hertz to the 100 Hertz. And if we bring the 100 Hertz back, we've got about 1.6 nanoseconds to get that trigger there. Again, very consistent with what we saw before. Let's bring the trigger point back to the center. And that's interesting, because that trigger point doesn't look exactly like I would have expected it to look. Wonder if I've got a delay from the trigger occurring. Pattern, mode auto. We're triggering at the beginning of the pattern. We don't really need to set a duration. We're just basically saying on a high, low, high transition, don't care. When the 4 of those are true, we grab a trigger. I'm not exactly sure. So this is obviously a PEBCAC error here. It's me not fully understanding the triggering menu here on the scope. But it doesn't really matter at this point. With time and practice, I'll get better at this, obviously. If we find one of the more interesting edges, this is the edge we were just looking at. Keep bringing it back over towards center. And of course, it's the same set of signals we were looking at a minute ago. So I find that kind of interesting. Let's back the time base down again and see if we can capture something else to trigger on. Let's go back to the trigger menu, pattern, and let's just go ahead and invert the pattern here. Him low, him transitioning high. And we'll just swap the pattern around. I believe I just inverted it. And we'll grab a single trace or single trigger. And we can see here that the most interesting piece on this is down here at this end. Oops, going the wrong way. Bring it back. Well, I keep rotating the knob the wrong way. And 2 nanoseconds resolution is the best we got here. And we've captured something similar to what we, well, identical to what we had originally, and that is where they all transition to 0. And again, 1.8 nanoseconds, a 1.8. In this case, they're all 1.8 nanoseconds where they tripped over to 0, which is interesting. So there's a little bit of, in my mind, some jitter here in this. But you know, they're all typically, so it looks like sub 2 nanoseconds. We had one out at 3.6. I'm sure some of this is the Verilog. I still question kind of how it's written. But you know, I'm learning. Hoping a little demo here and the setup with the logic analyzer maybe brought a bit more clarity to what's going on here. And I'll keep mucking in Verilog and sharing what I learn. We'll talk soon. Bye.